Hi everyone, welcome to this session of the summer class. Today we have Jakub Czukowski presenting MIMDRAM paper, which was originally presented in HPCA 2025. Yes, yeah. Sorry about that. This is a very interesting work bridging the gap into adoption of processing-using-DRAM. And the interesting thing is that Geraldo, who was the first author of this work, presented his PhD defense final presentation yesterday, and he has also a lot of other interesting works in the direction of processing using DRAM or near DRAM. So I also, additional to this paper, invite you to check those works if you're interested in this direction. So yeah, now you can present.
Okay, thank you. So hello, my name is Kuba or Jakub. And today I want to present to you MIMDRAM, which is an end-to-end processing using DRAM system for high throughput, energy efficient, and programmer transparent, multiple instruction, multiple data computing. That's a mouthful. Okay, so let's start with an executive summary of the paper. So the problem is that existing processing using DRAM architectures suffered from DRAM's large and rigid granularity. And that causes that the SIMD substrate to be underutilized, and we cannot take advantage of the parallelization available. We are only limited to perform mapping operations and cannot perform reduction operations, and it's rather difficult to program. So the goal is to design a flexible PUD system that can exploit parallelism at smaller scales, allows for in-DRAM data movement to support reduction operations, and lastly, provides a software infrastructure to ease adoption. So MIMDRAM is a hardware software co-designed PUD system that enables finer grained computation down from row size to just 512 elements. It adds cheap interconnect to support data reductions within DRAM. It allows for multiple instruction, multiple data execution just within DRAM, and provides compiler and OS level support to improve programmer experience. And the key results include the significantly better energy efficiency compared to state-of-the-art PUD systems, along that better than high-end CPUs or GPUs. And all that comes at a rather small area cost of about 1% to the DRAM chip and the CPU die. So let me first give you some background. So as we all know, the computation has become more and more memory bound in the recent years. Even as much as 60% of the total energy, system energy, is spent only on the data movement. So to address this, a lot of people have proposed multiple different processing in memory architectures. There are two main approaches that we differentiate. There is processing near memory, where we put the logic layer on the same die or close to the CPU or close to the memory. And there is processing using memory, which uses the operational principles of memory cells to perform computation. And MIMDRAM is the latter type. So some background on how DRAM is structured. First, we start with cells, which are organized in 2D grids of which we call mats. We have a local row decoder, which connects to the rows using the word line. And then we have the bit line, which connects, which allows for transferring data from the rows to the local sense amplifier. Then zooming out, we organize our mats in subarray. That's we put the multiple mats next to each other, and together they form a DRAM row. We also have a global row decoder that drives all the local, connects the global word line to the local mats. And we have the global sense amplifier that forwards the signal from the local sense amplifiers to the I/O interface, from which it can communicate the data to the CPU. So as some brief, how exactly does this DRAM row access happen is that we first send a precharge command, which prepares the sense amplifiers to read the data. Afterwards, we send an activate command to the row that we want to read the data from, and in turn that causes the sense amplifiers to sense the current variations in the cells, and that's how we can read out the value contained within cells. To actually perform computations in DRAM, we have to first know how to use the substrate. So first thing we will need is a in DRAM row copy. That is, we will copy one row in DRAM to another one. And we can do that by performing back-to-back activations to different DRAM rows. What happens is that when we first prepare the sense amplifiers, they're ready to sense the data. We activate the first row, the data gets sensed, and then we activate another row, and then what it makes it happen that the data gets fed back into the destination row 2. Another component that we will need is in DRAM majority operation, and this can be achieved by activating 3 different rows in DRAM simultaneously. And what will happen is that the sense amplifier will choose the majority of the 3 operands, which is a 0 or a 1. Together, these we can orchestrate these in DRAM row copies and majority operations to implement different circuits. For example, here we have a simple circuit that performs additions, and we can transform that to use only majority operations. And that's how we can actually perform meaningful computation inside of DRAM. It's important to mention that the operands are not stored in the row anymore, rather in the column. That means normally the data is stored next to each other in the same row, whereas now we will store the data within columns instead. Okay, so let me now discuss what are the problems that today's PUD systems face. So there are 3 main problems, and they all stem from the same root cause, which is the large and rigid granularity of DRAM. And the first problem is that we underutilize the available parallelism that DRAM provides us, which leads to throughput and energy waste. So we first will define a vectorization factor, which is how parallel a computation is. So for example, if you look here, this blue row, it doesn't use the whole DRAM row, which means that we cannot utilize the full parallelism of that the DRAM just accessing this whole DRAM row would provide. In the paper, the authors performed an application analysis to quantify available parallelism across and also within a single application, and we can see that majority of the applications parallelism is significant is below the row size, which is about 65,000 currently. And there's in some application, the available parallelism also varies just within that application. And this is the problem. So another problem is that we have very limited computation support. We're currently only restricted to perform mapping operations. So for example, given an array of numbers, we cannot collect the numbers and compute its sum, because the data is, we don't have any substrate to move the data between different columns. So if we were to add a direct connection between all DRAM columns within a subarray, that would lead, unfortunately, to significant area cost. So we won't be doing that. And last, the programming model of how to program a DRAM chip to perform useful computation is rather complex and problematic. So given this relatively simple loop that basically does conditioned addition or subtraction, this would translate roughly to this equivalent bulk binary operation code. And what the programmer is responsible for is for mapping and aligning the data, because we need to make sure that the data is row aligned. We need to identify array boundaries such that we can change the loop into these operations. We need to unroll the loop by hand, and we have to convert those addition to bulk binary operation add, for example, here. And lastly, we need to arrange for data movement, which is like we have those extra arrays here, that the E and F that were not present in the previous one. And this is rather cumbersome, error prone, and we will prefer that to be done automatically. So to this end, we propose the authors of the paper propose MIMDRAM, And the key idea here is to leverage this finer-grained granularity for PUD computation. And there are several key ideas here. First one is that we only allocate the appropriate computational resource as to avoid underutilization and have less energy waste. The second idea would be to concurrently execute multiple independent operations in different DRAM mats, that is to increase throughput. And lastly, we'll want to implement a low-cost interconnect to transfer the data between DRAM mats and DRAM and columns within a single mat with avoiding any CPU intervention. So let's start with the first one. We'll segment the word line. So there already exists a finer granularity than a DRAM row, and these are namely mats. So we reduce the granularity from about 65,000 to just 500. So the observation, we can just use the global word line, but can use the global word line, but also only access parts of the DRAM subarray. Then how to achieve the second idea is that we can observe that within the segmented word line, we can selectively interact with only a subset of the DRAM mats. And this will enable us the execution of different commands between different independent DRAM mats. And that will allow, in turn, for multiple instruction, multiple data execution model. And lastly, to implement a low-cost interconnect, we'll observe that first, there is already some interconnect that will allow us to transfer the data within a single DRAM mat, as well as there is already some interconnect that will allow us for transferring data across different mats. And yeah, we'll only perform minimal changes to enable that. So to summarize, MIMDRAM is a hardware-software co-design that enables finer-grained PUD computation at lower programming effort and low cost. And yeah, first now let me give you an example of how this intermat data reduction can be performed. So we want to perform a computation that is C equals A plus B, and we have 10 one-bit numbers spread over 2 DRAM mats. What we first do is compute the C1 and C0, which are the two parts of this reduction, which is the sum of those one-bit numbers. Afterwards, we can perform an intermat data movement, as in to bring the C0 part into the mat 1. And finally, we can perform the final reduction of C1 plus our temporary, which was the C0 row, C0 mat row. Now let me go over what hardware changes we need to do to enable all of this. So to enable segmenting the global word line, we'll add isolation transistors and row decoder latches, as long as alongside it mat selector that will allow us to selectively choose a subset or a subrange of mats that we will want to operate on. To allow for intermat data movement, we'll add a really lightweight layer of multiplexers. So these are basically 2-to-1 multiplexers that allow us to move the data from a neighboring mat to another one. And to enable moving the data within a single mat, we'll employ the help of the helper flip-flops, which are already available. And we'll do that by kind of violating how the operational principles of how they are normally used to move some data across different columns. Finally, to orchestrate all this operation, we'll need a control unit. This consists of a bulk binary operation buffer, which stores the instructions given to the system by the CPU. Which then we have the mat scheduler that will choose an instruction that can be executed by consulting the mat scoreboard, which gives us the information which matrices are currently available for usage, which mats are currently available for usage. And once we find a suitable instruction in our binary bulk operation buffer, we'll schedule this instruction to one of the microprogram processing engines, which will in turn start performing the execution. So now let me now go over the software component of MIMDRAM. So we'll start with some compiler support. And our goal is to automatically extract SIMD parallelism from source code and schedule PUD instructions to maximize SIMDRAM parallelism utilization. And we'll use, the paper uses existing LVM compiler infrastructure to implement 3 different classes, which I'll briefly discuss now. So we start with SIMD identification. So that means we look at the LVM intermediate representation and look for instructions that can be performed in parallel. We choose an appropriate vectorization factor that will give us the best throughput. And finally, we can also get rid of the data movement, since all the data now is resident in RAM, so there's no point in moving the data from memory to the CPU. The second step is to perform code scheduling and data mapping. So we construct the data dependency graph, which is this picture here. And it allows us to see the dependent operations and schedule them. And it's scheduled in the fashion we also need to map the operations to DRAM maps, similar in the fashion to how a CPU has to perform register mapping. And finally, what we need to do is generate the final binary by allocating the data and inserting appropriate bulk binary operation instructions. Now let me briefly mention the system software, the system support. This includes the instruction set architecture that includes operations such as additions, multiplications, gated like if-else statements. We also MIMDRAM also gives us an execution and data transposition support. As I previously mentioned, we have to transpose the data from the row format to the column format. We have to take care of data coherence because we need a lot more system use caches, and we need to make sure that we don't work against them. Finally, we need to perform address translations from virtual to physical addresses, and perform data allocations, alignment, mat label translation. And I will not go into more detail of these out of brevity. So when it comes to the evaluation, the MIMDRAM was compared to CPU, GPU, the previous work of the group, which is SIMDRAM, which is a PUD system, as well as DRISA, and also a Processing-in-DRAM system, which is Fulcrum. The researchers performed a 2-level analysis. First, they started with a single application, that is to measure how much intra-application parallelism the MIMDRAM can extract. And then that follows the multi-programmed workload analysis, which highlights how much inter-application parallelization can be achieved. So starting with single application workloads, MIMDRAM significantly improves energy efficiency, especially compared to the CPU, GPU, or the previous work of SIMDRAM by 37 and 14x, respectively. When it comes to multi-program workloads, even in the most optimistic case for SIMDRAM, where it uses bank-level parallelism, MIMDRAM is still 1.68 times more efficient in terms of throughput. And lastly, comparing MIMDRAM to other PIM architectures, MIMDRAM has significantly better performance per area compared to DRISA by about 1.18%, 1.18x, and about 1.92x compared to Fulcrum. Other results include that with subarray and bank-level parallelism, MIMDRAM is significantly more performant than the CPU and the GPU. It achieves comparable throughput to the other PIM architectures, and has, which was the main goal, it significantly improves the SIMD utilization compared to the previous work. And all that comes at a rather small area overhead of about 1% to both DRAM chip and the CPU die. And there are, of course, there's more thorough analysis in the paper. So now let me conclude. So to sum up, MIMDRAM is a hardware-software co-designed PUD system that enables finer-grade computation at low cost and easier programmability. The key idea was to leverage finer-grained DRAM for processing using DRAM operations. And in hardware, we made simple changes to allow MIMD execution and added a low-cost interconnect to allow in-DRAM data reductions. And from the software side, we added compiler support and OS level support to reduce the burden on the programmer. And yeah, we achieved significantly. The MIMDRAM achieves better performance, energy efficiency, and throughput compared to state-of-the-art PUD architecture, as well as CPUs and GPUs, and all that at a rather small area cost. Okay, finally, let me now go over some strengths that I have found in the paper. So first one is that I really appreciated that MIMDRAM is really aimed at driving the processing using memory towards wider adoption. They want to allow make it easier for programmers to shift into this paradigm of programming, even transparently, so that the programmer doesn't have to know. It's aimed towards more intelligent memory. So that means that the more and more logic is offloaded of the CPU die. It only includes minor hardware changes and simplifies the workflow for a programmer to make processing using DRAM system work. And finally, following the fact that it uses LLVM as its compiler support, this also makes this rather language agnostic, because a lot of other languages than C or C++ can compile down to LLVM. And there are unfortunately some weaknesses that I have identified as well. So I'll start with the rather ununified code identification and generation strategies. So what MIMDRAM does is it optimizes solely for throughput. So that means that whenever an instruction or a loop can be mapped to a PUD operation, it will do that. And it does not consider a cost model. So basically, it has a rather simple cost model. So the cost model is, I see an instruction that can be mapped to PUD computation, I map it to a PUD computation. And this is partially, the paper mentions it, why that's the case, and it's mostly attributed to LVM being not generic enough to support the variable SIMD width of MIMDRAM. The second issue I have identified is that the performance within multiplication or like more complex operation dominated workloads is worse than in a CPU or a GPU. That is caused by the fact that multiplication uses quadratic number of operations, because we need to, for example, an addition would only use a linear number of operations, because we need to simulate the whole adding circuit of n binary digits. Whereas for multiplication, as you know, like you perform multiplication on paper, it usually requires about quadratic number of steps. And the issue is that we cannot, since the goal of PUD computations is to improve throughput, we cannot always hide this high latency of the multiplication computation if it's not available. Then, while MIMDRAM adds a lot of flexibility, there are still some things that we cannot do. So the first thing is we cannot perform floating point arithmetic. The benchmarks that the researchers have run, they translated the floating point arithmetic to fixed point numbers. And another thing is that the global in-DRAM data movement is still rather limited, and that also limits how we can do the data mapping inside DRAM, because it's limited only to the neighboring mat, and is, as far as I understood it, is unidirectional. So we can only move the data from the left matrix to from the left mat to the right mat. And that is a source of unoptimized code scheduling and data mapping. So first of all, this code scheduling is, again, insensitive to the operation type. So for example, it will schedule the code the same way if we perform additions or we perform multiplications. And it follows a very relatively simple approach by just recursively following the leftmost path and mapping it to the same mat, and then recursively doing that for all the unmapped subtrees. But overall, I think that PUD is an really important research avenue, especially in the context of energy efficient systems, because the biggest advantage is that we achieved significantly better energy efficiency compared to the PUD, to the CPU or a GPU, just because we avoided a lot of data movement. The second takeaway I would say is that there are two different fronts that can drive the PUD adoption. So that first one is that we don't necessarily want to perform drastic hardware changes, because that will be an issue for the manufacturers to implement, and all the committees to convince that this is indeed what we want to implement. And the other is that we want to make it easier for the programmers to program these systems, for example, by hiding this fact pretty much completely by doing this automatically. And lastly, this paper highlights how we need to optimize across the entire software hardware stack in order to implement new ideas that have potential to change the principles of how we compute. Okay, so that was the paper part, and now I want to pose you some questions. So my first question to you is, given that MIMDRAM PUD generates PUD code with the goal of solely maximizing SIMD throughput, given sufficient vectorization factor, it always maps to PUD instructions, right? So what do you think we could also is this even the most optimal way to optimize code? What do you think? Or do you think that what would happen if the program is compute dominated? Is mapping always to PUD instructions always good? Can you come up with a scenario when it's not good?
Well, I have a question. Is it if you don't have a big vector or anything, you just want to do like two very simple a simple operation, is it always slower to use the CPU?
So
you have to get the data and everything, but
yes. So the question is whether it's always slower to use the CPU. Well, that depends. Again, that depends on how many things you want to perform at once.
Yeah.
So given that, first of all, we cannot use the system if the vectorization factor is, for example, smaller than the single mat, right? But then still, it's not necessarily always faster to perform all the computations within DRAM. Given, like, for example, we've seen multiplication takes order of n squared operations, whereas the CPU has that accelerated with some smarter hardware. So yeah, as I said, some PUD operations are really multiplication heavy and have bad latency. And my question is to you: what other metrics we can optimize for? What ideas do you have other than just pure throughput? Yeah.
Some quality of service metric. I don't have any in mind.
Service. But, okay, yeah. So like fairness and stuff like that. Okay, yeah, thank you.
Energy efficiency.
Energy efficiency.
Because in the end, if it's too energy inefficient, you can just clock up the CPU and do it on the CPU in the end.
Mm-hmm. Anything else? So we have throughput, fairness, quality of service, energy efficiency. Any other ideas? So we can also just strictly optimize for performance. So we can, as you said, mentioned already, it's not always worth to move the data to keep with the PUD computation model if we care for strict performance, right? that it may be more efficient to more performant or faster to move the data to the CPU, perform the computation and move the data back to the DRAM still this way. So yes, energy efficiency you already mentioned, and fairness, quality of service. Okay, so now given these, how can we optimize? Because we've already seen that MIMDRAM always maps to an PUD instructions, and this is because they don't employ any comprehensive cost model. So the paper mentioned that LVM IR is not expressive enough to represent the variable SIMD vector width. Do you have any ideas of how we can enable this more diverse, more precise optimizations? What can be done if we cannot use LLVM IR to represent those? What can we do instead? Yes.
Maybe use another compiler.
Okay.
Probably you have to change a lot, assuming I think MIMDRAM already implemented the framework, right? So you have to modify the entire framework to build on top of CLang.
Okay, so you can implement like a custom compiler, right? Yeah, that is perfectly possible. Any other ideas? Yep.
Manually annotate your code with some directives.
Okay, so we can manually, yeah, okay.
Do you want to say it again?
Okay, yeah, we can manually, we can do this whole process manually. Yes, that is a way, but yeah, that of course then removes we go back to the previous kind of state where we were already doing this manually. So yeah, so what are the alternatives? Yes, we already mentioned creating a new custom compiler, and we deemed that rather impractical. Another way is to maybe we take what LLVM already gives us and then just tweak it a bit so that it works. But my suggestion that what we could use is opt for a more flexible compiler infrastructure. I don't know how many of you have heard of MLIR. How many? Can we do a show of hands? Okay, 1, 2, 3. Okay, 4 people. So what is MLIR? It's a newer compiler framework. This stands for multiple level intermediate representation. And it allows to represent target specific operations, such as, for example, PUD operations. So what we can do is translate on MLIR allows for kind of mixed kind of instruction format. So we can mix in LLVM IR inside with some with this PUD kind of domain specific language. And that then allows us to perform more generic optimizations that are already, for example, available in this framework. Yeah, and it's already, so we can basically define a more finer cost models that will allow us then to optimize for different objectives. Yeah, so as I said, we can implement this PUD instructions as like a domain specific language that then we can interleave with the instructions, with the normal LVM instructions, and then define a more interesting cost model that will allow us to optimize for different goals. Okay, my next discussion point is how is CPU and PUD computation different in the principle? So we already know that the CPU performs computation using bit parallel arithmetic. So it's, for example, the addition doesn't take O of n time, it rather takes logarithmic or / constant time. It's accelerated. So we achieve low latency. So from the things you have heard already, what happens for, okay, maybe. So yeah, the operand bit size is usually constrained by hardware. It's usually 64 bits. Whereas with PUD, all operations are executed in bit serial fashion. So this means that additions take O of n time and multiplications take O of n squared time. And it's optimized for throughput rather than latency. So my question to you is, how can we potentially improve? What can be done to make this computation, this bit serial computation faster, since it seems that it's limited by the O of n and O of n squared? What can we do instead? how can we improve the latency of bit serial computation? So my hint to you is maybe what are the maybe inputs that we can do we always need to compute on fixed bit width? Does that spark something in your heads? For example, given that we have numbers, we know, for example, that our data set only contains numbers from 0 to 10, and we'll be adding pairs of those numbers. Do we need, what can we do, and what would be different from the CPU model? Yes?
Encode or map the data differently depending on the workload?
Okay, so you mean, for example, we can decide that our numbers fit within a smaller bit width?
Yeah. Let's say if you can fit one number in 8 bits, you can pack 3 or 4 of these 8 bits into a 2-bit, and yeah, this would be the encoding.
Okay, so what we can do instead of using like a fixed size of 64 bits, we can be kind of more data aware. And what we gain is that our addition no longer and multiplication no longer take 64 squared or 64 operations, but rather however long our operands are, right? So this is already one paper, the paper from the same authors already partially suggest these. So we want to reduce the bit precision for some of the PUD operations by allowing for narrower bit sizes. For example, for 10-bit multiplication, we only need to perform around 100 operations instead of around 16 squared operations. So what advantages can you think of? What disadvantages can you think of allowing for variable width precision? Like, for example, what happens to the data layout? What happens to the benefits should be relatively straightforward. As a first, we make it faster, right? That's pretty obvious. But what else? Maybe think how the data is not like. Assume we have some fixed size data stored by the CPU. For example, we have these 16-bit numbers, but we know that we'll only use the 10-bit numbers, right? So this allows us to potentially save some memory because we can map the data already to 10 bits, and we don't have to pay for the price of, for example, because normally we have to have byte aligned accesses, but this allows us to skip that, right? So these are like the potential advantages of this solution. So faster execution and potentially smaller memory usage. What do you think that the disadvantages would be? Yes?
There's some complexity involved in implementing this, I assume.
Yes, so that's exactly it. So as you remember, or maybe not remember, so I'll remind you, we have this, we have to transpose the data from bit parallel format, so row format, to this column format. So then that would make this logic, this hardware part, this part potentially more complex. So that's one thing. Any other ideas for what are the potential disadvantages here? Okay, so I'll spoil it to you. The PUD program, microprogram generation might be more complex because before we had what was happening, we had a fixed kind of instruction set. Now we have to, for example, we had like additions of 32-bit numbers. Now we'll have to support the bit width as part of this instruction microprogram generation instruction that maybe might have been not clear. Yeah. And my next question is, what can we do if we simply cannot accept or hide this latency of bit serial computation? So we know that given that we have that our data is, for example, it's 32 bits. It would fit exactly correctly, but that's still too slow for us. What can we do? Can you maybe think of some hybrid approaches? Also, maybe what if we want to support floating point arithmetic? How would we do that? And my suggestion is that we don't necessarily need to compute everything using DRAM. What can we do? Yeah.
Well, we can just use CPUs or the CPU to perform floating point arithmetic or latency sensitive applications.
Yeah, that's perfectly valid. So we'll use some type of hybrid execution that will, for example, mix PUD execution and CPU GPU execution. For example, since PUD doesn't support floating point, we will offload that work to the CPU. Can we think of a more memory-centric way of doing it? Yeah. So what we can add is processing near memory components, right? So exactly, that's correct. So we can add kind of accelerators for the operations that we really care. So for example, we can add accelerators for floating point arithmetic and for the slow operations of, yep.
Wouldn't it kill the purpose of the entire year if you were to send half the program, half the question, half the execution?
Well, that's the big problem of how can we actually make good use of it, right? So,
yeah.
So
I feel like at that point, you guys just send the entire execution of the CPU.
Well, that again depends. How do we know it would be faster? Maybe if it would be faster, we might as well do it. If it won't, like if we optimize for performance, might as well do it. If we optimize for energy efficiency, still might be better to keep it in DRAM. So yeah, it's rather difficult to kind of know how to best use how to leverage this. It's a lot of research has been put into it, and it's a really complex topic of how to eventually map these parts of computation to different components. And my last talking point would be how we can facilitate PUD adoption with SMD that we've heard actually a couple of weeks ago. So you can recall that SMD enables asynchronous in-DRAM maintenance mechanisms, and that SIM-DRAM operates at subarray granularity, while MIMDRAM uses MATS, which is one level lower. So how would you envision these two systems to work together, or what potential issues would you see? Any ideas? Yeah.
Well, if we rely on the DRAM to do calculations, then any locking to do maintenance operations could potentially increase the time it takes to actually compute.
Well, we already know that the maintenance operations have to be done one way or another. It's the question whether it's done by the DRAM itself or scheduled by the memory controller. So that technically shouldn't be an issue, because the maintenance operations have to be performed one way or another. So what would happen, for example, if we made SMD work at DRAM MAT granularity instead? Do you think that will be good, bad, slow, fast, energy efficient, energy inefficient? What's your opinion here? So the question is rather, do we pay too much for making SMD this granular, right? Is that going to be an issue? Any opinions? It's more of an open question without a definite answer.
Question.
Yeah.
What do you think would be
On the durability.
Do you think it would change anything, or do you think it would be slightly less?
So
Have no effect.
whether it would the computation would affect the DRAM durability, I mean, I don't know how to answer that exactly. But what I can say is that DRAM durability has not been an issue so far as a memory substrate. It's more of an issue with NAND memory, right? There, the memory actually degrades over time. Whereas in DRAM, that has not been an issue. But I cannot comment really. If it would be a problem, my guess is not much, because we just perform the usual operations that DRAM would perform either way, maybe a bit more often, because these are just row activations and the row and pre-charging the sense amplifiers. Do you think that in what way do you think that maybe SMD could make the MIMDRAM faster? Is there an avenue that you can see that would happen?
I suppose then you'd have a lot of the maintenance to be dealt with itself within the DRAM, and you could have a lot of computation and maintenance be dealt completely in memory and not have to have the CPU have any overhead on it.
Yes, that's
probably
one
slightly, yeah.
One way.
Say so.
Yeah, what we can also do is we can kind of we have this. If you recall, we have this math scoreboard, which basically denotes whether a math is busy with computation or not. We can maybe leverage that to also note down which maths are actually used for computation. Maybe we don't have to refresh the rows that are not used for computation. Given that, like, since we already have this scoreboard, might as well use it for more kind of DRAM management operations as well. So, for example, we can map we can collect the information which maths are actually containing operation like data, application data. Okay. So it's like integration, like OS level integration.
Yeah.
Anything else? So if not, that will be it for me. So yeah, I presented to you MIMDRAM, this long text, and thank you a lot for listening to me.
Do you want to say something?
Yeah, thanks for the presentation. Just a few points to add. So as you have seen, processing using DRAM or processing near DRAM can provide a lot of performance benefits. So it's a paradigm shift from the processor-centric mode of computing that we conventionally have been using. So to enable the adoption of this paradigm and facilitate it, there are a lot of interesting research that can be done, and a lot of problems that need to be solved. So Jacob presented some of them in the context of this paper, but there are still a lot more, as you can imagine, to be done. So if you're interested in these topics, feel free to talk with TAs in the course and people in the lab if you want to learn more or like be involved in solving some of these challenges. Yeah.
Maybe I'll comment one thing about DRAM reliability you ask. I think you were referring to row hammer or kind of read disturbance. So actually we have an upcoming paper on ISCA so that we show that this put operations where you activate multiple rows at the same time. So if you recall that row hammer is just you activate a single row at a time and then you sandwich a row basically. You activate the one aggressor and then you pre-charge, you activate another aggressor. And in between you have victim row. So here there might be a setting that maybe that's the rows that you're activating, maybe sandwiching a victim row. Basically you're activating multiple rows at the same time, which sandwiches a victim row. So actually over there we show that it's make things a lot worse, like more than, so we see that like 150x reduction in like the minimum time that you need to hammer. So that like empirically, yeah, and it is actually
present not just for simultaneous activation of multiple rows to perform measures. It's when you do row clone, even you get let's say less hammer count induced bit flips. Not necessarily row press. So row press is also different. So row hammer. Yeah. So here in row hammer, you keep the row open at minimum time, which is 36 nanoseconds, let's say. And row press, you keep the row open like longer, microseconds. But still, in both, let's say, attacks, you just activate only one row at that time. You keep one row open at a single time. So it's getting worse. And also another maybe aspect for not just put but PIM. So there's actually another upcoming paper to DSN, which shows that this PIM operations, row clone and PNM, PIM-enabled instructions actually increases the throughput of memory side channels and covered channel attacks. I guess that one is already on archive. You can check for amplifying main memory, let's say, covered and side channel vulnerabilities. So yeah, there are a lot to be done in terms of both in the stack and also in the robustness and reliability of DRAM-based systems, I think. Yeah.
Hello, everyone. Hello. Yes. So now we're moving to the second presentation. Presenter is Konstantinos. Konstantinos is a first-year master's student, and he got his bachelor's degree from the University of Athens. He's interested in computer architecture, and specifically his research interests lay with memory management and address translation. Feel free to start.
Thank you very much, Mail. Can everyone hear me? Yes, okay. So my name is Konstantinos, and I'm going to be presenting functionally complete Boolean logic in real DRAM chips, experimental characterization and analysis. This is going to be the outline of my talk. I'm going to start with some background. I'm going to give a general idea of the paper. I'm going to go into details, and we're going to look at strengths, weaknesses, and the discussion. First, let's see some background. We have seen this many times in the lectures, but this is a DRAM module. It consists of DRAM chips. Each chip has input-output circuitry and an array of banks, which are all connected with this circuitry. And this is the bank. We have a lot of subarrays and a lot of sense amplifiers, and each subarray has its own local row decoder. Specifically, this paper focuses on this region, the orange region, which is the array of the sense amplifiers that is between two neighboring subarrays. Now, DRAM manufacturers, in order to increase the capacity of DRAM, have employed a new architecture called open bitline architecture, which looks something like this. This means that from the bottom subarray, column 0, 2, 4, etc., is connected to the sense amplifier from the bottom part, and from the top subarray, column 1, 3, etc., is connected from the top part. This way, we have half of the sense amplifiers that we have otherwise. But we face the problem that how is this going to work? We are connecting the sense amplifier, both the top subarray and the bottom subarray. So when the top row is activated, we have to make sure that we cannot activate any row from the bottom subarray so that we don't have interference. Essentially, the top data will be negated. So we do not want to touch the bottom connectors in any way. So we do not activate any row in the bottom subarray. So just a little foreshadowing, this looks like a NOT gate, but we're going to see how this is going to work later on. So let's see at the DRAM operations, all the DRAM operations. We have our subarray, we have our sense amplifiers, and the first operation of DRAM is the activate operation. We choose a specific row, and we fetch the data and amplify them into the sense amplifiers. The second operation is read-write. We connect a specific column of the sense amplifier to the input-output circuitry. And finally, we have the pre-charge command, which actually prepares the bank for the next activation. Usually it's done before the activation because we want to have the data as much as possible into the sense amplifier to issue read and write commands, as many as possible. So between these commands, we have some specific time constraints. So the manufacturers have said that we need to keep a specific amount of time between each command, and this is going to play a role later in the presentation. So let's see what this paper is about. First of all, let's look at the motivation. We know that data movement from the lecture is a really big performance and energy bottleneck. And previous work has shown that processing using memory operations can alleviate this problem. We can do the processing in memory and not have all the data movement that we would normally have. So the problem is that current work in processing using memory, and especially the ones that focus on commercial off-the-shelf DRAM chips, lack the NOT operation. The NOT operation has not been shown. Lack the NAND and NOR operations, which also have not been shown. And despite having AND and OR operations with 2 operands, we do not have AND and OR operations with multiple operands. So this work aims to propose mechanisms for these operations, leveraging the open bitline architecture that we saw. And they will evaluate these mechanisms with 280 DDR4 chips from 3 different manufacturers. And these are some preliminary results of the self-DRAM chips perform NOT operation and multi-input operation with more than 94% accuracy. And this is shown in commodity chips, which is really important. Let's look at the key mechanism quickly. First of all, they show how to simultaneously activate rows from 2 neighboring subarrays. We're going to see that in detail later. The NOT operation in of-the-shelf DRAM chips and the multi-input operation in of-the-shelf DRAM chips. But in order to understand exactly the mechanisms, we need to know how they experimented on the DRAM chips. So this is the testing infrastructure. It was used before in DRAM Bender. It's based on this work. And we can see that we have a host machine, a desktop essentially, an FPGA board, which controls the operation of the DRAM and controls the DRAM and the timings in which these commands are issued. And we have a DRAM module. Clamped onto it are some heating pads, which essentially heat the DRAM to the temperature that we want. And we control this temperature through the temperature controller, which has probably a thermostat and detects the temperature and regulates it. So the authors tested 208 DDR4 chips from 3 manufacturers, as mentioned before, with a plethora of parameters, speed rates, chip densities. We're going to see them later. But the DRAM manufacturers were SK Hynix, Samsung, and Micron. But not every manufacturer supported every single operation. As we see, SK Hynix supported both operations, both NOT operations and multi-input operations. Samsung supported only the NOT operation that the authors proposed, and Micron didn't support any of them. Now, the authors do give an explanation about why this happens. It's actually a hypothesis from a previous paper that says that when we violate the timing constraints, I talked about the timing constraints before in the commands, when we violate these timing constraints and we put commands really close one to the other, we can see that sometimes the chips do not even issue these commands. So the Micron chips do not issue some specific commands if some timing constraints are violated. So essentially, we cannot do these mechanisms because we cannot issue the commands in the correct timing. Now, let's focus and see the heart of the paper, which is essentially the key mechanisms. And we saw before there are 3 key mechanisms: simultaneous multi-row activation, the NOT operation, and multi-input operations, NAND, NOR, AND, and OR. We're going to look at them in detail, and then we're going to have some small results for every single one of them. First of all, simultaneous low activation. This actually is necessary in order to build up the other 2 operations. So we have 2 neighboring subarrays. The first step is we need to activate a row from subarray X. We activate row A. Then, as normal, we need to pre-charge the specific row, but the manufacturer actually has proposed a specific timing window in order to do that. The authors violate this timing window. So they do the pre-charge command really close to the first activate command. Next, we have an activation in the other subarray. And again, we do not keep the proposed timing by the manufacturer, we violate it again. So what we have is 2 violations of the timing constraints, and this mechanism supposedly will activate more than 1 array from these 2 neighboring subarrays. So in order to understand exactly how this mechanism works and which and how many rows were actually simultaneously activated, the authors did all the combinations of row A and row B. So they tried with every row from subarray X and with every row from subarray Y. And they noticed they had some observations. The first observation they had is we can simultaneously activate multiple rows from one subarray to another from 2 neighboring subarrays that are close by, that are neighboring. The second observation was that these activations had a specific pattern. This means that when n rows were activated from the first subarray, exactly n rows were activated from the Y subarray. So we had the 1-to-1 ratio. This was the first activation pattern. It was very distinct. And the second one was when n rows were activated in subarray X, twice as rows were activated in subarray Y. That means we have a 1-to-2 ratio. And these patterns were so distinct that they had a notation. And the authors gave this the name n to n. And to the second one, they gave the name n to 2n. And it's important to keep that in mind because the key takeaway that they had from these observations was that when we had the n to 2n pattern that we just showed, the number of n, the maximum number of n was 16. That means that a maximum in two neighboring subarrays, we can activate 48 rows simultaneously, which is a really interesting result. And I'm going to say why I find it interesting later in the talk. So once we have this done, we can move on to the actual mechanisms that perform the useful operations. First of all, we have the NOT operation. So we have one cell from the first subarray and one cell from the second subarray. We suppose that the source cell is charged to 0 for this example. And first of all, we activate the specific row. We see that at the beginning, we know that the connectors have a voltage of VDD over 2. Then we pre-charge without violating the timing constraint. So what we notice is that the top connector has a ground because the source was 0 before. So the top connector has a voltage of ground. And because the bottom connector has the negated value, we see that it has a voltage of VDD. Under normal DRAM operation, this doesn't affect the destination cell at all because we haven't activated anything and the voltage doesn't pass to the destination cell. But the authors issue an activate command and they violate the timing constraint. That results in the cell slightly charging and charging and charging. And finally, when we issue the pre-charge command, the destination cell is fully charged. As you notice, the source cell has been negated to the destination cell. We have a NOT gate. And it's in DRAM. And they tried to experiment with this. So they did a sweep of the parameter space. They tried so many chips and they tried different row numbers. They tried different temperatures, different number of destination rows, different distances from the sense amplifier, and different speed rates, die sizes, and a lot of other parameters. So let's see a little bit some results for this specific NOT operation. Now, we start with defining the success rate. So the success rate is the number of successful attempts divided with the total attempts. So if we make 100 attempts and 10 of them work, we have a 10% success rate. Let's kind of explain the box chart, which is a complicated chart. We can see that this is a number of attempts with different success rates. And the small little circle is the mean of all the attempts. The line is the median of all the attempts, and the top, the box contains 50% of all the attempts, which is the majority of the attempts, and the bottom and row line is actually the maximum and minimum. There are some outliers as well, but they're considered outliers. There are a small amount of them. So let's look at the trend. So as the number of destination rows increases, we can see that the success rate drops. But despite having this effect, it makes sense because we have more destination cells, then the sense amplifier will not be able to charge all of them, up to 232 of them. But we can see that in every case, there is at least one cell that is successful, that has a success rate of 100%. That means at least one cell in the entire subarray can perform a NOT operation. Then we see the temperature. The temperature, and this is a really positive thing, the temperature doesn't affect the operation at all. So even in a high range of temperature, for 50 to 90 degrees Celsius, we see a 0.2% variation. And specifically in the 32-row case, which is the worst case for the NOT operation. Then we see the speed rate. The speed rate is chaotic. There is no trend to the speed rate, and it's an interesting result. We can see that in this specific case, when the speed rate is low, we have a range of success rates. When the speed rate becomes bigger, it's the medium speed rate of the three, we see that it's the worst. It has the worst success rate. And in the biggest speed rate, the success rate, for some reason, increases. And this is all for the NOT operation. And we're going to move on to the multi-input operations. First of all, in order to multi-input operations, we need to have some cells in the top subarray, which we call the reference subarray, and we set them in order to set the operation. And the bottom one is the compute subarray. We put our operands in the bottom subarray one by one. Now, the initial setup is that we charge one cell in the reference subarray as 1 and one cell as half. Now, this half charged cell may seem weird, but it's proposed in a previous work called fract DRAM. And actually, in commodity of the self-DRAM chips, we can have a cell that is half filled. It's neither full nor empty, but it's half. And the authors leverage that to perform the multi-input operation. So we activate both the top, all the cells that you can see. We activate all the rows that you can see, and we violate the constraints between them. So we activate the top, we precharge, we activate the bottom, all violated time constraints. And we notice that in the connectors, we have the average of all the cells. So the average of all the cells in the reference subarray is 3VD/4 in this specific case. And the bottom one is X plus Y/2. Now, depending on what the value of the voltage is, we can have two results. If the average in compute subarray is bigger, we can see that the voltage is dropped downwards. That means that the sense amplifiers pull the voltage downwards towards the compute subarray. If the average is smaller, then the sense amplifiers pull the voltage upwards towards the reference subarray. And thus we can differentiate between a 1 and a 0. Let's see it in a little bit more detail with a truth table. So we take the exact same setup and we see that X and Y is 0. In this case, we see 0 voltage at the bottom, so the voltage is pulled upwards. Again, in this case, Y is 1. Again, the average is not bigger, so the voltage is again pulled upwards. Again, with X only 1. And with X and Y equal to 1, the voltage this time is pulled downwards. We can see that the average is bigger, it's VDD in this case. And what you may have noticed is that the reference subarray is an AND gate, and the compute subarray is an AND gate. So we have successfully done an AND gate and an AND gate. And the same with the OR gate. I'm going to focus on the setup mostly. We can see that in the reference subarray, we have one cell that is completely empty and one cell that is half filled. And we can see some examples. If they're both 0, if X and Y is both 0, both the operands, we can see that the average at the bottom is 0, so the voltage is pulled upwards. If only Y is 1, the voltage is pulled downwards. The voltage at the bottom connector is more than the voltage at the top connector. And again, when X is 1 and when both X and Y is 1, again, the voltage is pulled downwards. And as you have noticed, the reference subarray is an OR gate and the compute subarray is an OR gate. So we have both an OR and an OR gate. But what about multi-input? I'm showing two inputs through this entire presentation, but there's the setup. I'm going to show specifically the setup. And for the end reference subarray, we have to fill all the cells with 1 and one cell half. So if we do that and put our operands in the compute subarray, we're going to have an AND or AND gate. And about the OR, we fill all our cells with 0, except from one that we fill it halfway. This way we can have multi-input AND, NAND, NOR, and OR operations. So let's see how the authors experimented and what were the results. How robust is this operation? So again, they shown different row numbers, different temperatures, different number of destination rows, different distances from the sense amplifier, and different speed rates and die sizes, again. And these are some of the results. Let's begin with the number of operands. Now, this is a counterintuitive result. As the number of operands increases, then the success rate rises. Now, this is interesting and happens because this mechanism's problem is when the voltages are close, the voltages at the top subarray and the bottom subarray are close, the sense amplifier cannot sense the difference and cannot pick which subarray the voltage will be pulled to. So when we have more operands, we have more opportunities, if you think about it, for this distance to be smaller. So many cases in the 16 number of input operands case have a bigger difference between the compute and the reference subarray. So that's why this is detected more easily and the success rate increases. Let's see at the temperature. The temperature again has minimal effect on the robustness. So these operations are really robust in terms of temperature. We can see from ranges to 50 to 95. We see small variations, mostly in the OR and NOR case when we have two operands. So this plays almost but no significant role. And finally, the speed rate again is chaotic. There's no trend. We can see here, we see a smaller difference between the medium and the low and high speed rates. We see a bigger one here. And for some reason, in the NAND gate, there's no difference. The speed rate doesn't play any role and the success rate is up. So to conclude, the authors had three major contributions. They simultaneously activated multiple rows from two neighboring subarrays, and they managed to activate up to 48 rows. They managed to do the NOT operation in of the self-DRAM chips with a success rate on average of 98%, and they manage multi-input operations with a success rate of 95%. Now, this is all for the mechanisms. We're going to move on to the strengths and weaknesses, but if you have any questions, please tell me. Wait for the microphone.
How easy is it to control the VDD by 2 volt voltage in a row? I think that was used for the NAND and OR NOR case.
What do you mean how easy it is?
I'm assuming that you need some specific access pattern to set a VDD by 2 voltage in a row.
Yeah, the details are more on the FRAC DRAM paper. I'm going to scroll through the slide, but the details are in the FRAC DRAM paper, but needs a series of operations in order to have this half cell, similar to these operations in this paper.
Could it be better to do, for instance, if you wanted to do a two row operation, and you need a 3 VDD by 4 on the reference subarray, could it be better to have 3 rows of VDD and 1 row of 0? Would that possibly give you a more reliable 3 VDD by 4?
This could possibly work, but this is also one of the weaknesses of the paper that we saw, that I will talk about later, is the fact that these are extra rows. These are not rows of operands. So we're taking, and imagine this row is 4 kilobytes long. So you're sacrificing 4 kilobytes just to have more. And the half in this case plays a really important, plays a really neat role, because it allows this whole thing to happen. If I think it would work, Ismail might have to correct me, but I think this might work. But I don't know how robust, and if it's going to be more robust in this case, or if you have Philosophy.
I see.
Yes.
Thank you.
I would consider it even being more robust, but who knows? Anything else? Any other question? Please. Here.
So I still have a question. What accuracy refers to? Is this like per bit or per word or per line?
The success, it was the success rate, right?
Yeah.
So the success rate is, if we're doing X total attempts for this specific thing, I think for cells, we're looking at the cells specifically. If we do X attempts, we see which of these attempts the cells were correct. So we count cells essentially. We count how many cells we did the operation to and how many of them were correct. So this is essentially the success rate.
I have one more question.
Please.
Do we copy data into these rows to perform computation because it's destructive?
It is destructive, yes, and this is another weakness of the paper. And we do have to do some form of copy. We need to keep our data twice.
Like something like row clone?
Something like row clone, or the CPU can actually put the data twice, or leverage row clone. They don't leverage row clone, but it could be that.
So in that case, it would be safe from retention concerns, or I mean, leakage concerns of these rows, because the reference value has to be quite accurate for you to perform good reliable computation.
Yes, there are issues with robustness, obviously, because the average is more than 98 and more than 94. It's not 100%. So the fact that you copy the row, I don't think has anything to do with the mechanism. The fact that you keep the copy there, it's mostly in the total sense, in the fact that you have to put the rows somehow there in the correct place, in the correct rows. So I don't think it helps with success rate. But still, success rate is not 100%. And when you are doing computation, this needs to be taken into account. Yeah. But still, it's a really good number for a NOT operation. Any other questions? No. So let's move on to the strengths and weaknesses. First of all, the strengths. It was the first paper that introduced functional completeness in DRAM, in off-the-shelf DRAM chips, in DRAM chips that we can buy. There is functional completeness if we violate the timing constraints. As we saw, they showed not multi-input NAND NOR gates that didn't exist, multi-input gates that didn't exist before. Also, they had a really thorough experimentation setup. We saw that they did a sweep of the parameter space. They checked so many chips. They checked 280 chips with a lot of different parameters. So their evaluation was very thorough, very solid, And they shown that these things can actually happen in commercial chips, in commodity DRAM chips. Next, something that I found really interesting is the fact that in order to do their operations, they introduced a way to simultaneously activate rows from two neighboring DRAM subarrays. And this mechanism can be leveraged not only for this mechanism, but for other different mechanisms. Maybe for a copy, maybe for all of this. And I think this is gonna be a really good tool in the hands of a DRAM researcher in the future. And finally, they did no modifications. Previous works have shown how to modify DRAM and have an operation with modifying the DRAM, but this work did it in commodity chips. And I think this is really important for demonstration purposes. But let's move on to the weaknesses. First of all, the methodology has significant memory overhead. We can see that for every operand, we need an extra row. So, and these rows are, as we said, maybe 4 kilobytes, they are long. So we're sacrificing this space during the computation in order to have these extra rows that actually serve us nothing. And we have to initialize them. And it's a general hassle, the fact that we have to have all these extra rows. And also, after computation, the data that we had in the compute row, as you mentioned, is destroyed. The result overwrites the data, both in the extra rows and the compute node rows. That means that all our setup in the extra rows and all our operands in the compute nodes are gone. So we have to copy, we somehow copy and rewrite them, and it has a memory overhead. That's the definition. Then it has an intuitive input format. What do I mean with that? First of all, because we leverage the open bitline architecture, we saw that, for example, at the bottom, the columns 0, 2, 4, and so on and so forth are connected to the sense amplifiers. That means that our data need to be put there in order to do the computation. What happens to the other columns, though? They're underutilized. Maybe we can put something there. Maybe there are a lot of uses, and I'm going to have them in the discussion, but these are not used for the computation. So we have half the row to use to do actual computation. And then we need to have this format somehow. We need to take our data. I have disconnected this row. And so that if we have our data in this format, we need to do this conversion. We need to take the data and spread them around. And this needs to pass through the CPU, or we need to change the DRAM in order to do this conversion. But still we have a penalty. So I think this is a real weakness of the paper. And then it's not applicable to all manufacturers. They gave an explanation why, a hypothesis why to be exact, but it's not applicable to Samsung and Micron manufacturers. And the Samsung, the node operation is supported by Samsung. But I mean, this is a strength and a weakness because it was mentioned in the paper. It was mentioned the fact that these manufacturers, we cannot make it work. And we tested it and it's not possible. So it's a strength and a weakness. And finally, the speed rate doesn't make any sense. Why does this happen? Either there is a huge correlation with the speed rate, so these operations are either really sensitive to the speed rate or have nothing to do with this. And this is just statistically insignificant, just randomness. But in N and OR, it plays a huge part. In NAND, in many operands, we see it plays no part. It is weird. Are there any questions about strengths and weaknesses? No? So we move on to the discussion. Okay. So first of all, what are other operations that can be implemented using the same open bitline DRAM mechanism? We have a bulk way to do these operations. We have this NAND, these OR gates. How can we leverage them? How can we leverage them differently to do useful computation? Any ideas? No, I didn't suppose so. Okay, so I would propose bulk value initialization. We can put our values in the X operand, and we can leverage our trusty NOR or OR gate, and we can do it. We can copy the result in many rows, 32 to be exact, in maximum. So, and we can do it in a bulk way. We can do it for many columns. So bulk value initialization could leverage the open bitline in order to do some useful computation. Then, how can the operations presented in this paper be orchestrated on the CPU side? Now, this is a big question. It is based on SIM-DRAM and MIMDRAM. How can we do a similar architecture? We presented, I think, MIMDRAM 2 weeks ago. How can we do a similar architecture in order to also orchestrate these operations? And how would the operand movement look like? How could we move the operands to a specific place? We said row clone. Anything else? How could the operands be allocated? When the page fault happens, we need to know this place is for operands. How are we going to do that? How are we going to signify to the OS that? No idea. How could the programming model look like? How would the ISA look like? How can we do the data formatting? I mean, SIM-DRAM and MIMDRAM have a component in the memory management unit, in the memory controller. Please.
It could be quite similar to.
No, continue.
It could be quite similar to MIMDRAM. You could just have it done at the memory controller where you move the data, you unpack the data into the format relevant for. What's it called?
So when we throw something off the cache, the conversion actually happens at this specific place, and we flush the caches, and the format takes place at the memory controller. Yes, exactly. Yeah. It could be done there.
For the operand allocation, do you mean doing it? Do you mean like what rows in the subarrays, or?
Exactly. How we're going to put the rows, and how is the CPU not going to put data there? Because in order to do the computation, we're actually reserving some specific rows. How are we going to do that?
The memory controller again, because you need to know the address mapping, right?
Yes. Is the memory controller aware of the address mapping? So we need somehow to communicate to the memory controller that this is the address mapping, this is used for computation, this is used for in-DRAM computation. It would be interesting. Please, you have the question.
Yeah, I think I had a similar input, but maybe an idea would be like to reserve a whole bank just for the operations, and then use it a bit like a vector register.
Yes, this is overdoing
that's wasteful, I guess.
Yes, it's overdoing it because we actually reserve an entire bank for as long as our computation, or maybe forever, depending on how you're going to reserve it. But yes, this could be really interesting. Yes, please.
I would guess, just as in the MIMDRAM paper, one could use operating system support to block certain parts of memory as computational or relevant for computation based on what the program runs. So depending on the operations, one could have certain rows as off limits, and thus enable like not as much of a big memory overhead as preserving an entire bank, for example.
Mm-hmm. Yes, but and I have a follow-up question on that. Do you think you should integrate these operations in the SIM-DRAM model, or do you think they require a different? Because they're special. The operations used in SIM-DRAM, MIMDRAM are a majority, and we have changes in DRAM. Do you think we should integrate these operations inside the same architectures, or should we have a different one?
I mean, one could use the same ideas as in SIM-DRAM, since most of the operations are similar, and probably the way you would compute things would also be similar. I'm not quite sure about whether like the specific control structure, like the ISA extensions, how well they would map to exactly this. Mm-hmm. But in general, yes, the data layout could be like similar to SIM-DRAM. Maybe one would have to adjust for the like slide spread, as you mentioned, but that should not be like huge work.
Yes, you're right. Yes, it could be done. Anything else? Okay, so the next point is, how can we leverage the unused cells? We talked about it. How could the unused cells, the half of the cells in the row, could be leveraged? Any ideas? Maybe save irrelevant data, or we could split the data in half. We could do the entire computation in the row. We could put have the data in the actual computation, and then put the rest of our data in between and do the computation with the subarray below. And put the subarray below, but we could do that and actually take advantage of 3 neighboring subarrays and do the and use all the row if possible, because the subarray in the bottom is connected like the subarray on the top in this graph. So the other columns are connected with the bottom sense amplifiers. So we could leverage both of them, possibly. And finally, how do you think the evaluation of the mechanism in real workloads should be tackled? Is this more energy efficient at the end of the day? Is this more performant? How could this be tackled? How we should evaluate this? Or any specific domains that this could work? No? So this could work maybe on genomics, on graph processing applications, something that can be highly parallelizable, embarrassingly parallelizable. And yes, and I think there is a lot of application. I think this could be a really interesting thing to evaluate, whether there's actual energy gains to be had. And with that, I wrap up the presentation. Thank you so much for your attention. What now? Any comment, Ismail?
I'll maybe ask a question to you, actually.
Please, please.
Can you go to your last discussion point? No, maybe the third one then. So you propose to use half of the cells and the bottom subarray and place data there. Where do you put the reference cells?
On the bottom, on the other subarray, on the third subarray.
Okay. Does that really increase the utilization, or is the underutilization coming from the fact that you have to have reference cells?
Yeah, the thing that it actually helps with, because it has a destructive nature, either way you were going to put data in their reference subarray, in this reference subarray, if you did twice, if you move data. So the only thing that you gain is the fact that you move the data once. You put the data in the middle rows, you put them only once. So you don't have to copy. Because it has destructive nature, you were going to form 2 reference subarrays either way, either serially or parallelly. So then you just save the time to do the formatting and to put the data twice there.
Okay, fair enough.
But so I'm not sure if I understand the open bit line correctly, but when you have data in the cells in between, and when you perform the activations for all of those, won't your data get corrupted in the cells in between?
But you're going to have no, and I don't think they're going to get corrupted. I'm not sure. I'm not 100% sure of that.
There's a bit line running along, right? Or am I mistaken?
That's true, but I don't think they're going to get corrupted if you don't, because you're not having a sense amplifier connected at this point, at this column, at the specific column.
Okay.
So I think the data is going to be put on the sense amplifier, amplified, and then put back on the cell normally. I think.
Okay. My intuition is that I would just average all the values in those cells, and then
there's no connection between the columns.
No, the one single column.
Yes.
So let's say you're activating 4 rows together. The 4 cells, all of them have different values.
Yes.
And they're connected by the bit line, right?
Yes. That's the mechanism.
Right. So the 4 values, the bit line will have the voltage of the 4 voltages on an average. Won't that affect the value?
On the columns, we have the operands. The problem is the other column, the next column, which is not connected to the operands column at all.
Okay. I'll think about it again.
Anything else?
You want one more?
No. Please.
Okay, I think you asked this question also. Maybe it was not quite clear, your answer in that case. To ask it simply, how do you make sure the value, the voltage value, half VDD, is maintained at half VDD for the cells that you initialize with using fractional operations?
I'm not really familiar with frac DRAM that much, but I think it's maintained in the Frank DRAM paper. First of all, we don't know that it's half VDD. We take it in a side channel way, the fact that it's half VDD, but I think it was kept. They checked it exactly after by not violating the time constraint. So if you do it last, maybe it will last. It will last long enough to do the computation.
Yeah,
and it's not also 100% half VDD, I think.
Yeah, that's. I think that's the idea. Also, you do it right before you start your computation, so you want to make sure half VDD is almost.
Okay, I want to ask an open-ended question. So now you see all this functionality in the commodity DRAM chips, and we can get benefit out of this, right? So now assume that you're designing the next generation of DRAM chips and you can do modifications. So what kind of modification would you do to make these operations more useful and more reliable?
These specific operations? Or other operations that are functionally complete?
Well, if you're interested in other operations, you can talk about them as well.
Okay. I think it would be more beneficial to do a majority operation. I think if we change the DRAM, we should do a majority operation. But if we don't change the DRAM, we want to increase the success rate of this specific one. First, we need the way to put reliably half voltage on a cell, which is difficult in itself. I think it would be a really difficult modification to do. And then we need to have sense amplifiers that actually amplify the difference better. If there is even the slightest difference, they will need to pull at the correct point. I think that would be the two main changes. Yes.
Big systems. But it is kind of surprising that we haven't done anything to fix it for a very long time in real systems, I mean. As far as I can remember, the paper that we wrote, the initial versions of it at least, or the earlier versions got rejected 2 or 3 times from major conferences. And the reason never was, oh, you are not fixing the problem that you showcase here. It's always like, how will this work with cache coherence? How will prefetching affect it? Which are, I consider auxiliary sort of smaller problems that you have to introduce whenever you propose a new technique. And then work that follows your work might fix that, right? So, I mean, to summarize, I guess, I'm a bit sad that nothing has been done to fix this inefficiency in real systems, as far as I can see. And second, when you change a lot of things, like Lorenz mentioned, like sector DRAM does, you face a lot of resistance from reviewers specifically. So be careful, I guess. Okay, that's the things I wanted to say. Do you want to add anything to that?
But still, you can change a lot of things. That's how progress happens. If you don't change anything, there is no progress. I'll make a comment about maybe this. So I was surprised that you didn't put making this reliable as a direction like here I mentioned. Is that not interesting? Clearly you have concerns about reliability.
Yes, there are concerns about the reliability, but I think the architectural part is more important. Because if we cannot orchestrate and integrate it with actual workloads and have a way for the entire stack to propagate and have real computation in real DRAM chips, then the reliability part we saw that it's quite reliable, and if we do some minor modifications, we can assume that we can go to 100% reliability.
How do you know?
I don't.
Okay.
But I would consider that would be easier than actually integrating this in the entire stack. That would be my argument, but I don't know if it's correct.
Usually the last mile is the hardest to walk.
That's true. Yes. But also integrating into every single program that the users use throughout the world is also quite.
But you don't need to integrate into every single program, right? You just need to show benefits in some important ones.
That's true. Yes. But still, a way to program would be interesting because these are just violating the timing constraints with an FPGA board.
Yeah,
It's
certainly.
really important, but it doesn't show the use inside the workload.
Yeah. Yeah, but I think the interesting part of this work is really demonstrating that it's possible in existing DRAM chips.
Yes.
I think later work should really take advantage of it and show how to make it reliable, how to make it usable. And these go hand in hand, probably.
Robust.